So we have so far completed the discussion of classical statistical mechanics, whereby we introduced and detailed on the concept of ensemble formalism, and we are by the time familiar with the three common ensembles used in statistical mechanics. The microcanonical ensemble, where the macro state is described by constant values of n, v and e, used to analyze isolated systems, which is regarded as an ideal case of system behavior. Then we learned about the canonical ensemble formalism, where the macro state of the system is defined by constant values of n, v and t, the temperature, where we permitted the energy of the system to fluctuate, keeping the temperature constant. And we have seen that ensemble formalism is best suited to analyze systems which are in equilibrium with an energy reservoir or in thermal equilibrium. So in canonical ensemble, the energy fluctuations are permitted. And finally, we came across the grand canonical ensemble, where the macro state is specified by constant values of mu, the chemical potential, the volume and the temperature. And we have seen that grand canonical ensemble is especially useful to study open systems, where both energy exchange as well as particle exchange is permitted, or where both the energy as well as the particle number of the system is permitted to fluctuate between any values 0 to infinity. And finally, we concluded that the results given by any of these three ensembles will be converging, or they will give identical results in the thermodynamic limit. And we proved that fact by considering the relative root mean square fluctuation of energy as well as the number of particles or particle density in the thermodynamic limit. And we have seen that in the thermodynamic limit, these fluctuations are inversely proportional to the square root of the number of particles in the system, which is pretty high. And we could also discuss the fundamental concept like the partition function. We have seen that it is the partition function which plays the major role or the central role in the ensemble formalism. Three different partition functions were defined in the three different ensembles. In the microcanonical ensemble, the thermodynamic probability omega was identified as the microcanonical partition function. In the canonical ensemble, we had defined QNVT as the partition function, canonical partition function. And finally, in grand canonical ensemble, we have identified Z as the grand canonical partition function. And the relevance of grand canonical or microcanonical partition function is that all the thermodynamical properties of the system can be obtained once we know the partition function of the system. So we concluded the partition function of any system in the ensemble formalism acts like the bridge to thermodynamics of the system. And in the classical systems like harmonic oscillators or maybe the classical ideal gas case, we could derive or we could establish the standard results by treating them as a member of these ensembles. So that is what we had done shortly in the previous classical statistical mechanics topics. Now we are in a state to extend the ensemble theory to study the behavior of quantum mechanical systems. That's what we're going to do. So module 4 in a way is a beginning of discussion of quantum statistics or quantum statistical mechanics. That's what we are going to discuss. So what we're going to do is that we are going to extend the ensemble theory that we have practiced in module number 1, 2, 3 to study the behavior of particles which are having quantum behavior or quantum mechanical systems. And in this topic, we begin with considering the behavior of three different types of distributions. Which are namely the Maxwell-Boltzmann or classical distribution, the Bose-Einstein distribution, and the Fermi-Dirac distribution, of which you have learned and you have discussed something in your undergraduate courses. Okay, and for convenience of doing these discussions, for convenience of studying the behavior of these three particle categories, we assume or we consider a system of non-interacting gas. We are going to consider a system of non-interacting gas as the sample, as the example on which we are going to develop the three different statistical distributions, namely the classical distribution known as the Maxwell-Boltzmann distribution, the quantum distribution known as, there are two quantum distributions, one is the Bose-Einstein distribution and the other one is known as the Fermi-Dirac distributions. So in order to introduce these distributions, we are going to consider a system of non-interacting gas. So a system of non-interacting gas is otherwise known as simple gas in statistical mechanics. Non-interacting gas. So you know that when we neglect the interactions between gas molecules, the classical ideal gas behavior was becoming easy to do, right? So we neglected the intermolecular intermolecular attraction. So you know that in the case of ideal gas, the total energy was becoming purely kinetic. So we could neglect the potential energy part of the total energy of a gas system only due to the assumption that the ideal gases were non-interacting. അപ്പോൾ നമ്മൾ അങ്ങനെ ചെയ്ത ഒരു നോൺ ഇൻട്രാക്ടിങ് എന്നുള്ള ഒരു അസംഷൻ എടുത്തത് കൊണ്ട് ആ അസംഷൻ 100% കറക്റ്റ് അല്ല നമുക്കറിയാം. ഓക്കെ, സോ സംഭവിച്ചത് എന്താ വെച്ചാൽ നമ്മുടെ അനാലിസിസ്, മാത്തമാറ്റിക്കൽ അനാലിസിസ് ബിക്കംസ് വാട്ട് ക്വൈറ്റ് സിംപ്ലിഫൈഡ്. So the same formalism or the same assumption we are going to continue in the discussion of quantum systems as well, like fermions and bosons, right? And we are going to treat the quantum particles as also a system of non-interacting gas. Means bosons do not interact between themselves or fermions do not interact between themselves. Okay, so we actually are doing an oversimplification of the reality, but later this oversimplification can be justified under certain conditions. And from this simplified model or from simplified distribution, finally we will be able to arrive at the case of real system behavior by just accounting for this simplification by some corrections, like we have done in the case of classical ideal gas. You know, the behavior of real gases deviate much from that of ideal gas, and then finally, you know, okay, we are just making a simple equation of state by correcting by van der Waals correction and all. We go from the ideal gas equation of state to van der Waals equation of state or real gas equation of state, and the same type of modifications can be done at the end. But for a beginning which is mathematically simple, mathematically appealing, it is always good that we start with simple gases. And by, remember, the simple gas in statistical mechanics means that the system of gases where the word gas has got a wide meaning, system of particles. By gas we mean system of non-interacting particles. So that is the meaning to be taken in statistical mechanics, a system of non-interacting particles. So the particle can be classical particles like the gas molecules. It can be particles like quantum particles such as bosons. So it can be bosons. It can be gas molecules as usually we consider. It can be fermions, etc. So we consider all these collection of particles, classical as well as quantum particles, as a system of non-interacting gas. And then we develop the thermodynamic behavior or statistical behavior of these collection of particles. by applying the ensemble formalism. So that is what we call as the theory of simple gases. So once again I repeat, by simple gases, don't just restrict your concept only to gaseous systems. We consider even a collection of bosons and fermions, which are quantum particles, as a system of behaving like a system of gas. Gas in the sense that, see, don't consider that, no, see that like bosons are just flying like the gas molecules and fermions are flying like gas molecules. No, okay, so just means that these fermions, for example, you consider free electrons in a metal. We are using the word free electrons in a metal. You know that compared to the what you call the valence shell electrons, or compared to the inner shell electrons, the free electrons are loosely bound, and they are having greater energy compared to the inner electrons, so that these electrons have got some sort of a freedom to move like free particles in a sea. So we call that one as electron sea, and like a sea of electrons, and these electrons can just flow freely, having greater energy. അപ്പോൾ ഇത്തരത്തിൽ എന്താണ് വളരെ ഫ്രീ ആയിട്ട്, അല്ലെങ്കിൽ എന്താണ് തമ്മിലുള്ള ഇൻട്രാക്ഷൻസ് ഒക്കെ മറന്നുകൊണ്ട്, അല്ലെ തമ്മിലുള്ള ഇൻട്രാക്ഷൻസ് ഒക്കെ നെഗ്ലിജിബിൾ ആയിട്ട് കരുതിക്കൊണ്ട് ഒരു ഫെർമിയോൺസിനോ അല്ലെങ്കിൽ ബോസോൺസിനോ ഒക്കെ സ്വതന്ത്രമായിട്ട് വിഹരിക്കാനുള്ള ഒരു സ്വാതന്ത്ര്യമുണ്ട് എന്നുള്ള അസംഷനിൽ നമ്മൾ അവരെ എന്താണ് ഒരു ക്ലാസിക്കൽ ഐഡിയൽ ഗ്യാസിലെ ഗ്യാസ് പാർട്ടിക്കിൾസിൻ്റെ അതേ സ്വഭാവ സവിശേഷതകൾ അസ്യൂം ചെയ്തുകൊണ്ടാണ് സിമ്പിൾ ഗ്യാസ് എന്ന ഗണത്തിലേക്ക് പെടുത്തുന്നത്. അപ്പോൾ ഇവിടെ ഓർക്കുക, സിമ്പിൾ ഗ്യാസ് എന്ന് പറയുന്നത് സാധാരണ ഗ്യാസ് എന്നുള്ള അർത്ഥത്തിലല്ല. ഓക്കെ, അത് ഗ്യാസ് ആവാം, പക്ഷെ ബോസോണുകളെയും ഫെർമിയോണുകളുടെയൊക്കെ ഒരു കണക്ഷനെ, അവരുടെ അന്യോന്യമുള്ള ഇൻട്രാക്ഷൻസ് നമ്മൾ നെഗ്ലക്ട് ചെയ്യുകയാണെങ്കിൽ അവരൊക്കെ ഒരു ക്ലാസിക്കൽ ഐഡിയൽ ഗ്യാസിൻ്റെതിന് സമാനമായ എന്താണ് ക്വാണ്ടം ബിഹേവിയർ കാണിക്കുന്നു എന്നുള്ള ഐഡിയയിലാണ് നമ്മൾ ഇവരെയൊക്കെ സിമ്പിൾ ഗ്യാസുകളായിട്ട് കൺസിഡർ ചെയ്യുന്നത്. സോ വിൽ ബി നൗ യൂസിങ് ദ ടേംസ് boson gas and Fermi gas. So remember, we will be using the terms boson gas and ideal Bose gas and ideal Fermi gas. So there, by gas we mean that we neglect the mutual interaction between bosons, the mutual interaction between fermions. So we completely neglect this interaction, and so we can regard them as having some sort of an ideal gas behavior. Okay, so we'll take up the topics one by one. So in a way, we are starting with the quantum statistical mechanics. So in order to begin with, as an introduction to the quantum statistical mechanics, we can just once again revise our idea of classification of particles. Okay, so already you are familiar with this particle classification in your undergraduate courses. Many a times you are discussed in your nuclear physics or your particle physics. You are very familiar with that. I just introduce it only to make our discussion complete. Okay, so you know that in physics, especially in particle physics, we divide or we classify the known particles, basically the elementary particles that we are coming across, into two broad categories. The two broad categories are classical particles and quantum particles. Okay, so all the known particles in physics are generally belonging to either category of classical particles or quantum particles. Okay, and what is the speciality of classical particles? You know, the classical particles are considered to be identical particles. So the classical particles are considered to be identical particles, which are considered as distinguishable. So we'll say identical and distinguishable. So this is the the speciality, the characteristic feature of what is known as classical particle. They are considered to be identical. They are considered to be distinguishable. Okay, they are also known by another name, since most of the behavior of classical particles can be explained by what is known as the Maxwell-Boltzmann statistical tools or Maxwell-Boltzmann distribution. So we call classical particles also as Maxwell-Boltzmann particles. So MB particles in short. So when we refer to MB particles or Maxwell-Boltzmann particles, we mean as system of identical and distinguishable particles. Okay, and see, these particles are obey. They are named as MB particles because they obey, you know, what is known as the Maxwell-Boltzmann statistics. They obey what is known as the Maxwell-Boltzmann statistics. And what is meant by obeying Maxwell-Boltzmann statistics? It just means that it is obeying a set of rules, a set of statistical rules. So that is just the meaning, a set of statistical rules proposed by Maxwell and Boltzmann. That's all. That's only idea. Okay, they obey MB statistics means MB statistics is nothing but a set of statistical rules that is proposed by Maxwell and Boltzmann. Okay, so those are whoever. So just like that, I can compare what is MB statistics. We can say that MB statistics is nothing but the constitution. Okay, so in a way, if you compare it with the ordinary terms, it is a constitution that is bound by, or that is obeyed by, obeyed by constitution, obeyed by Maxwell-Boltzmann particle or classical particles. Okay, classical particles in the Bharanaghadanayana Maxwell-Boltzmann statistics in the Manslakum. Okay, so every classical particle is bound to obey the rules, the set of rules, or they are not permitted to violate any of the rules given by Maxwell-Boltzmann statistics. So that is the meaning of that. They obey MB statistics. And shortly we will be deriving what are those rules and how do they differ from the quantum particles behavior. Okay, now coming to the other broad general category of particles named as the quantum particles. Okay, we can say that basically the quantum particles are identical. They are also considered to be identical. They are considered to be identical, but because here it was and indistinguishable, but here they are indistinguishable. Identical but indistinguishable. So that is the speciality. The indistinguishability of particles is the speciality of quantum particles. And you know that the classical particles being considered as distinguishable was actually a very an oversimplification of the real fact. Okay, even gas molecules, you know that gas molecules. So the example for a classical system is molecules in a gas. So even the molecules in a gas cannot be distinguished from one particle to the other. You cannot distinguish one oxygen atom or with the other one. All are identical actually. But for developing the theory of these particles in the very beginning of statistical mechanics, or we can say that at the time of development of kinetic theory of gases, okay, these particles were considered to be distinguishable, and still we just make that one as the same criteria. But later it's understood that actually these particles should not be considered as distinguishable, and that is actually an error or an oversimplification that we did historically. And you know that while we discussed the behavior of classical ideal gas, while during the derivation of what you call the entropy of classical ideal gas, we have seen that this particular assumption of distinguishable particle nature created some problem in our derivation of entropy, which we identified as a paradox known as Gibbs paradox. Okay, so the Gibbs paradox in the entropy calculation of classical ideal gas was only due to this oversimplification that we have been following historically, and later it was corrected, okay, by what is known as the correct Boltzmann counting, is it not? So we have seen that you have to divide by what is known as n factorial. An ad hoc factor n factorial had to be introduced in the counting of microstates. Thereby we could correct the Gibbs paradox and all. So there is a part of the history. Okay, but still the theory was developed as classical particles are distinguishable. And later you know that all these oversimplifications can be corrected by suitable modifications done mathematically, like the Gibbs correction. Okay, fine, good. So that is a clear distinguishing feature of quantum particles. The quantum particles are also identical. All the particles are considered to be identical, and of course they are considered to be indistinguishable. Okay, and moreover they are governed by So these quantum particles are controlled by, governed by what is known as quantum mechanical rules. And you know, the quantum mechanics is an entirely different realm where there are different sets of rules. You know, the particles are bound to obey special rules. Okay, that is depending on the intrinsic property of particles known as the spin. So we can say that the concept of spin is supreme. The concept of spin decides, or the property of spin decides the behavior of particles belonging to quantum particles. Okay, so we can say that this is spin dependent behavior. That is the speciality of quantum particles. And whereas in classical particle there is no any mention of the property known as spin. We don't talk about a property of the particle known as spin when we discuss classical particles. And so that is one reason why we always say that spin is a property of quantum mechanical origin, or only while you discuss the quantum property of the particles, we are bound to give due importance to what is known as what the spin. Okay, sorry. So they obey the laws of quantum statistics. That is okay. No, the thing you have to understand. Now, since it is found that the quantum particles are behaving differently, so different quantum particles are behaving differently. So finally, you know that these quantum particles are now broadly classified into two other categories, which are now named as what? The bosons and the fermions. And you know that what are bosons? These bosons are primarily they are quantum particles, so they are identical and distinguishable. So here we can say that they are identical and distinguishable. Identical and indistinguishable. Fermions are also identical and indistinguishable. I'm just using some short forms. And these what is a clear distinction between bosons and fermions? These bosons do not obey, they do not obey what is known as the Pauli exclusion principle. I'm writing in short PEP. So the bosons need not obey Pauli exclusion principle, and the fermions must obey, they obey Pauli exclusion principle. Okay, and which you know, so it is regarding what is known as the accumulation of particles in the same quantum state, right? Okay, not more than number of particles can accumulate in the same quantum state. So you know that that's all depending on whether it is a fermion or a boson, or in other words we can say that it was identified that the bosons are characterized by what is known as what in terms of the spin, they are characterized by integral spin. Bosons have integral spin, whereas the fermions are characterized by half odd integral spin. Half odd integral spin, or half spin, we can just call that. Okay, it can be 1/2, 3/2, or 5/2, all in units of h cross. Okay, so the spin is integral here, and the other one is for half odd integral spin. And so in order to study the behavior of bosons and fermions, which are behaving differently, even though they are both quantum particles, a set of different rules were framed for these two categories, which are nowadays known as the Bose-Einstein statistics or Bose-Einstein distribution. So the Bose-Einstein distribution, and this one is this set of rules were framed by Fermi and Dirac, known as the Fermi-Dirac distribution. So in a way you can say that bosons are obeying, or bosons obey the laws of Bose-Einstein distribution. So that is a simple way of defining what is bosons. So bosons are those particles which obey the Bose-Einstein distribution, which is a set of statistical rules framed for integral spin particles. And fermions obey the Fermi-Dirac distribution, which is the set of rules framed for particles having half odd integral spin. Okay, and both of these categories must in general obey the quantum quantum mechanical rules. So you have got a number of examples for these bosons and fermions, and we'll be dealing with the bosons and fermions in detail in 2 other modules, which is going to follow. Okay, so which is ideal Bose systems and ideal Fermi systems. It will be quite straightforward once you go to those 2 modules. And you know that the most common example of boson is photon. Okay, so photons means any quanta of electromagnetic radiation. It can be a photon of visible light, photon of X-ray, photon of gamma ray. So any photon, okay, means a quanta of energy, you know, okay, of electromagnetic spectrum. That is a photon. So all photons are bosons. Okay, so you can see that in a sense we can say almost half of the particles in the universe are named after an Indian physicist. Okay, Bose. So we can be proud of being Indian in the sense that half of the particles in the universe have been named after an Indian physicist, Satyendranath Bose, right? Now photons. Now another common example is phonons. Phonons. Okay, phonons are also bosons. So phonons, you know that they are the quantum of vibrations, the quantized vibrations, phonons. Okay. In solid state physics, you will come across the behavior of phonons also. So there are so many examples. So phonons are 2 common examples of bosons, right? Similarly, when you come to the case of fermions, you have all the familiar elementary particles like electrons, the most common particle that we come across. Elementary particle, electrons. All electrons are fermions. Okay, then protons, the constituents of atom, the main constituents of atom, protons, neutrons. So this is something that we can clearly remember. Protons, electrons, neutrons, the basic constituents of an atom, all the 3 are fermions. So these 3 particles will be having half-odd integral spin. Okay, you can just always relate with that one. So they are all thick: electron, proton, neutron, etc. So you will come across a more number of such particles in our later discussion of ideal Fermi and ideal boson systems. So that's regarding the general classification of particles and distinction between the 3 different types of distributions. So in the discussions that we are going to do in coming lectures, we will be developing the necessary theory for each of 3 categories differently. So we'll be developing a theory for classical particles or MP particles known as the Maxwell-Boltzmann distribution. We'll be developing a theory for quantum particles separately for bosons and fermions. So for bosons, it will be known as the Bose-Einstein distribution, and for fermions, it will be known as the Fermi-Dirac distribution. Okay, and we will be finally discussing how these 3 systems will behave differently, or why do these 3 systems behave differently. Okay, and this can be done by using our ensemble formalism, okay, modified to suit for quantum systems. So we will start off our discussion by considering the quantum mechanical microcanonical ensemble of ideal gas. Or our first topic will be to consider the behavior of an ideal gas in quantum mechanical microcanonical ensemble. Okay, so remember, in the theory of simple gases, what we are going to do is to extend the ensemble theory to study the behavior of quantum mechanical systems, and thereby developing the 3 different types of distribution. That is our ultimate aim, by considering all particles, whether it is classical particles or quantum particles like bosons and fermions, as non-interacting particle systems or ideal gases. Okay, ideal gases or simple gases. We are going to develop the the 3 statistical distributions. So we will see, or we will do that one in the next lecture. Thank you.